Join us as we explore Karl Popper's fascinating thought experiment that challenged our understanding of quantum mechanics and the uncertainty principle. This experiment sits at the heart of one of the most profound debates in quantum physics. What causes quantum uncertainty? Before we dive into Popper's experiment, we need to understand Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that the product of position uncertainty and momentum uncertainty must be greater than or equal to h bar over 2. This means the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. When we know the position precisely, shown here as a narrow region, the momentum becomes highly uncertain, shown by particles spreading in many directions. But the crucial question that Popper addressed is, why does this happen? What is the physical mechanism? There are two main ways to interpret the uncertainty principle, and this is where the debate begins. Interpretation A from the Copenhagen school says uncertainty arises from our knowledge. When we measure or know something, we disturb the system. In this view, the act of measurement itself physically disturbs the quantum system, causing the uncertainty. Interpretation B, the realist view, says particles already have uncertain properties regardless of measurement. It's intrinsic to nature. In this view, the uncertainty is built into the fabric of reality itself, independent of whether we measure or observe. Karl Popper designed an ingenious experiment to distinguish between these two interpretations. Popper's setup uses pairs of entangled particles, which are quantum mechanically connected. Two particles, A and B, are created in an entangled state, meaning their properties are correlated. Step 1. We measure the position of particle A very precisely through a narrow slit. Particle A passes through a narrow slit, which gives us precise knowledge of its position. Step 2. Because the particles are entangled, measuring A's position tells us about B's position without directly measuring B. Step 3. The crucial test is whether particle B's momentum distribution spreads out, even though we never directly touched it. This setup leads us to the fundamental question Popper wanted to answer. Does particle B's momentum spread simply because we gain knowledge of its position through the entanglement? Is it our knowledge alone that causes the spread, or must there be a physical interaction? Or does the spread happen only if we actually physically interact with particle B itself? Let's use a helpful analogy to understand this distinction. Imagine a drop of ink in water. Does observing it cause more mixing, or does actual stirring cause mixing? Scenario A. You simply observe where the ink drop is. Does this observation alone cause it to mix more? Scenario B. You physically insert a probe to find the ink. This clearly causes physical disturbance and mixing. The quantum question is analogous. Does knowledge alone cause quantum spreading, or only physical interaction? Let's look at the mathematical framework that describes this situation. For particle A, when we measure position precisely, making delta XA small, delta PA must become large. As delta XA approaches 0, delta PA approaches infinity by the uncertainty principle. For entangled particles, there are position and momentum correlations between A and B. The position of B is related to the position of A by some distance d. For momentum conservation, the momentum of B is opposite to the momentum of A. The Copenhagen interpretation predicts that knowing XA through measurement means we automatically know XB. Therefore, delta XB goes to 0, which means delta PB must go to infinity, even without touching B. Let's work through a concrete numerical example to make this clearer. Suppose we use electrons with typical quantum scales for our experiment. Planck's reduced constant h bar equals 1.05 times 10 to the negative 34 joule seconds. Initially, both electrons have some uncertainty in position and momentum. Let's say the initial position uncertainty is about 10 to the negative 10 meters, roughly atomic scale. The initial momentum uncertainty is h bar over 2 delta x, which gives about 5 times 10 to the negative 25 kilograms meters per second. Now we measure particle A by passing it through a narrow slit. The slit constrains particle A's position to about 10 to the negative 12 meters. By the uncertainty principle, A's momentum uncertainty increases to about 5 times 10 to the negative 23 kilograms meters per second. Notice this is about 100 times larger than the initial momentum uncertainty. The critical experimental question is, does particle B also show this 100-fold increase in momentum spread? Different interpretations make different predictions about what we should observe. The Copenhagen interpretation predicts, yes, particle B should show increased momentum spread just from our knowledge of A. Knowledge of A is transferred through entanglement, causing B to spread according to Copenhagen. The realist interpretation predicts no, particle B should not spread unless we physically interact with it. Without direct physical interaction, B maintains its original narrow momentum distribution. What happened when physicists actually performed variations of this experiment? In the 1980s and 1990s, several groups performed experiments testing Popper's ideas. The experimental result showed that particle B does indeed show increased momentum spread. However, there's a crucial subtlety in interpreting these results. The debate shifted to distinguishing between information about spread versus actual physical spread in the system. The results revealed an even deeper paradox about the nature of quantum mechanics. The fundamental paradox is, what do we actually mean by the physical situation of a quantum system? Does the quantum state represent physical reality itself, or just our knowledge about reality? This question sits at the heart of quantum mechanics. Is the quantum state real, or just a description of our knowledge? The modern consensus is that the wave function is the physical state, but this raises new questions. When we measure A, the combined wave function of A and B collapses into a product state. Measuring A changes the joint quantum state, which affects B instantaneously, even at a distance. Popper's experiment connects deeply to Bell's theorem and quantum non-locality. Bell's theorem proves that no theory with local hidden variables can reproduce all quantum predictions. Classical theories obey Bell's inequality, where S must be less than or equal to 2. Quantum mechanics predicts S equals 2 root 2, about 2.83, violating the classical bound. Popper's experiment tests whether gaining knowledge about A physically affects B's state. The correlations between measurements on A and B show non-local quantum connections that classical physics cannot explain. Both Popper's insights and Bell's theorem point to quantum non-locality as a fundamental feature of nature. These abstract questions have concrete implications for quantum technology. Quantum computing relies on entanglement and the precise nature of how quantum information works. Understanding how measurement and knowledge affect quantum states is crucial for quantum computing. Quantum cryptography uses entanglement to create provably secure communication channels. A deep understanding of quantum measurement is essential for developing quantum technologies. Why does this philosophical debate about knowledge versus reality matter? This debate reveals the fundamental nature of physical reality at quantum scales. Quantum reality is fundamentally non-local, meaning distant parts of a system can be instantaneously connected. It profoundly challenges our classical intuitions about causality and how information works in nature. It demonstrates that measurement in quantum mechanics is an active physical process, not passive observation. Let's summarize the key insights from Popper's quantum experiment. Popper proposed an experiment to test whether knowledge alone causes quantum uncertainty or if physical interaction is required. He cleverly used entangled particles to separate the effect of knowledge from direct physical contact. Experimental results showed that changes to the quantum state affect the entire entangled system. This revealed that the quantum state represents physical reality itself, not merely our information about it. The interconnection of measurement, entanglement, knowledge, and reality forms the foundation of quantum mechanics. The philosophical debate about the nature of quantum reality continues in modern quantum foundations research. Popper's experiment teaches us profound lessons about the nature of reality. Quantum mechanics forces us to fundamentally rethink what we mean by physical reality. At the quantum level, knowledge and physical state are deeply intertwined in ways that defy classical intuition. This shows how deep philosophical questions can have concrete, testable experimental consequences. The quantum world remains mysterious and counterintuitive, continually challenging our understanding of nature.